In this video, we will discuss few problems which are very important for different kinds of exams like CSR Night Gate, KSET, and Assistant Professor. So here the first problem is the energy eigenvalues of a particle of mass m confined in a one-dimensional box of length L is. So this is the general energy expression for a 1D box. En is equal to n square h square by 8 ml square. Here n is the quantum number which takes values 1, 2, 3, something like that. And in this expression, if you substitute this equation, h bar is equal to h by 2 pi, then you would get the answer n square pi square h bar square by 2 ml square. So the answer for this question is option C. So this is a general energy expression, and use this as substitution, then you will get this answer. The other problem here is the commutator of x square px square is equal to. To solve this problem, we need to be knowing a few important relations for this commutator relations. And if A, B, C are the operators, then the commutator of this form A comma the product of two operators B, C is written as is equal to B times the commutator AC plus commutator AB times C. Now this B would come onto left, then we are left with AC, that is written here. Then this C would come onto right, then we are here left with AB. So the commutator of this form can be written like this. And the other equation we should know to solve this is this. The commutator x power n with px is equal to n x power n minus 1 I h bar. Now this is the given commutator expression. X square comma commutator x square comma p square is written as x square comma a product of p into p, where p is the momentum operator. Then you can expand this commutator according to what is shown here. The commutator a comma product of two operators. Here the product of two operators is same. Then you can send this p onto left. Then we are left with x square comma p commutator x square comma p, plus then you can take this p onto right. Then you are left with commutator x square comma p. Now we should write this p as it is here down. Then the value of this is according to this equation. You can write 2x power 1 I h bar plus now this value also is 2x I h bar. Now we have p here. Now what is common in these two terms is 2I h bar is common. Take 2I h bar outside and 2I h bar outside. Then what is that we are left with is p into x plus x into p. So p into x and x into p, you cannot add them together because they are operator. In case of operators, a into b is not equal to b into a. So the one which is matching is option C. Now here is one more problem. It reads like this. Let psi x be an arbitrary wave function of a physical system and h be the Hamiltonian of the system with its lowest eigenvalue denoted by E naught. So which is the relation which is correct here? In this case, this is the expectation value of the energy. Expectation value of the energy is always greater than the true ground state energy, or with the lowest energy eigenvalue in it. The expectation energy is always greater than or equal to the true lowest eigenvalue, or you can also say that the expectation value based on the arbitrary wave functions and the defined Hamiltonian is always greater than or equal to the true ground state energy. So the relation which is correct here is option D. So there is the expectation values of energy will not involve this square and square root and square, and this cannot be equal to less than equal to the true ground state energy. It would always be greater than or equal to the true ground state energy. So the next problem here is a quantum system is in the state 1 by 2 pi 1 plus 1 by 2 pi 2 plus 1 by 2 1 by root 2 pi 2 plus 1 by 2 pi 3, where pi 1 is equal to, it's a quantum mechanical state where I varies from 1 to 3 are orthonormal. The probability amplitude for the system to be in the state 1 by root 2 pi 1 plus pi 3. Now we will take this to be psi 1, the entire the linear combination of the basis wave functions. This phi 1, pi 2, phi 3 can be taken as the basis wave functions. The linear combination of this basis wave function will now be taken as psi 1, and the other linear combination of the basis wave functions phi 1 and phi 3 is taken as psi 2. Then the probability of finding this psi 2 is psi 2 star psi 1. You can write the probability of finding the system in this state is equal to psi 2 star psi. This is the probability of finding the system in this state. In this state is psi 2 star psi 1. Now, before this we doing, now if we have two terms like this, a plus b into a plus b plus c, then after multiplication you will get 6 terms. You just keep multiplying this a into a square, a into b, ab, something like that. So in that case, what we could see here is these are the cross terms, ab, ac, ca plus cb are the cross terms. We can take this to be cross terms. Cross terms tend to 0. Cross terms tend to 0. Only thing we are left with the terms of same basis function. The terms of the same basis function. This similarly, when you write this psi 2, a linear combination of 3 basis functions, and psi 1, a linear combination of 3 basis functions, and psi 2 is a linear combination of 2 basis function, and simply multiply here. So this is nothing but just doing multiplying psi 2 star with psi 1. Then we are now left with only 2 terms, because this is a 2-term function, and say this is a 3-term function. When you multiply, you will get the cross terms will get cancelled. The similar terms only we are now left with here. So 1 by root 2 into 1 by root 2. So this is my psi 2. So with respect to the phi 1 basis function, 1 by root 2 into this is 1 by 2, 1 by 2 phi 1. Now with respect to phi 3, the coefficient here is 1 by root 2, 1 by root 2 into 1 by 2, 1 by root 2 into 1 by 2. Then psi star, psi r phi 3, phi 3, phi 3 star, phi 3. The other cross terms should become equal to 0. Then from the given conditions of orthonormality, the integration of psi star psi or the expectation value, the integration of the psi star psi is equal to 1, and this is psi star psi also is equal to 1. Now we are left with 1 by root 2 into 1 by 2 plus 1 by root 2 into 1 by 2. So this will become equal to 2 by 2 root 2, and 2 root 2 gets cancelled. We are now left with 1 by root 2. The answer for this question is 1 by root 2. It is just multiplying this function with this function and make sure that the cross terms will get cancelled, and we are only left with the basis functions of similar basis functions. Phi 1 star phi 1 with these two coefficients plus phi 3 star phi 3 with these two coefficients. Then you simplify, you get the answer. So in the next problem, the number of ways in which 5 identical bosons can be distributed in 4 states is. For bosons, the number of ways for arranging 5 bosons in 4 states is given. For bosons, this is the expression for finding the number of micro states, n plus g minus 1 factorial by n factorial into g minus 1. N is the number of states, n is number of particles, n is number of particles, and g is the number of energy states, and g is the number of energy states. So we have how many particles? We have 5 particles. The n value is 5 and g value is 4. You can substitute in this equation 5 plus 4 minus 1 by n factorial into g minus 1 factorial is 3 factorial, and it would come to this value. So in these many ways, these five identical bosons can be distributed in 4 states. You must remember that for bosons, we will follow this formula for finding the number of ways of arrangement. For classical statistics, we may have the other. For classical particles, distinguishable particles, we will use this formula n factorial into this multiplicative summation taken over all the levels indicated by I of gi power n divided by ni. So this is the formula we will use for finding the number of ways of arranging particles according to classical statics. You can take it to be classical, or you can take it to be Maxwell-Boltzmann distribution, or you can take it MB statistics. Maxwell-Boltzmann statistics for calculating the number of ways of arranging n particles in G energy levels. So here is one more problem. Suppose we have two non-interacting identical bosons, both of mass m. We have two identical bosons of mass m in one-dimensional infinite square well potential in the range 0 less than or equal to x less than a. The wave function when one of them is in ground state and the other is in the excited. So this is a square well or a 1D box with the length 0 to a, and this is the ground state described with this quantum number n is equal to 1. This is the first excited state described by the quantum number n is equal to 2, and we have one particle, one boson in the ground state and one particle in the excited state. And what is shown here is this is the psi n is equal to root 2 by a sine n pi x by a is the general wave function of a particle in a 1D box. Now, as we are in 1D box, but our particles now present in the one particle is in ground state, the other one is excited state. So the wave function associated with this state is psi1 is equal to root 2 by a sine. Instead of n, we can place n is equal to 1. And when you place n is equal to 2, you will get the wave function associated with this particle. So psi1 and psi2 are the wave functions associated with this particle. When you place n is equal to 1, you will get the wave function for this particle. And when you place n is equal to 2 in this general expression of the wave function, you will get the wave function of this particle present in the first excited state, which is having the quantum number n is equal to 2. Then total wave function of this system, the total wave function of this whole system is the product of these two, psi1 and psi2 will give the total wave function of the system. And also, as bosons have integral spins, they are symmetric with respect to exchange. They are symmetric with respect to exchange, or they are symmetric with respect to exchange operator. Then we can write the same wave function, the total wave function psi, as 1 by root 2 psi1 into psi2 plus psi2 into psi1. It is symmetric with respect to exchange of particles. If it is asymmetric with respect to exchange of particles, then what we should write is psi1 into psi2 minus psi2 into psi1. As bosons have integral spins, they are symmetric with respect to exchange. Then we can write psi1, psi2 plus psi2, psi1. This negative sign here will not come because the particles are now bosons. They are symmetric with respect to exchange. So now this is the total wave function psi1 into psi2 plus psi2 into psi3 into 1 by root 2. So when you multiply these two, you will get 2 by a. And when you multiply these two also get 2 by a. 2 by a will be common, and 2 by a will be common, will come out 2 by a, and here we have in the denominator root 2. This 2 by root 2 is written as root 2. So the correct answer for this question is C. Just have written the wave function corresponding to this particle and the wave function corresponding to this particle just by placing n value is equal to 1 and n value is equal to 2 in the general wave function equation. We will get these two. When you multiply these two, then you will get the total wave function. And then with the concept of bosons, they are symmetric with respect to exchange. Then we can write the total wave function will get modified to psi 1 by root 2, psi 1, psi 2 plus psi 2, psi 1. So the correct answer is this C. In this problem, we need to find the average energy of an ensemble of gas molecules in equilibrium is given in terms of partition function. We need to write the average energy of gas molecules in terms of the partition function. The answer for this equation is average energy is equal to, in terms of the partition function, is equal to minus dou ln z by dou beta, where z is the partition function. That's what is the partition function, average energy, or you can also write, take it to be internal energy. That's what is the partition function, and beta is defined like this. Beta is equal to 1 by kBT. This is the one form of expressing the average energy in terms of the partition function. The other form of average energy is average energy is equal to Kb, where Kb is the Boltzmann constant, and Kb is Boltzmann constant, Kb T square into dou ln z by dou T. So this is the other form of writing the average energy in terms of the partition function. So these two equations can be used for writing the average energy in terms of the partition functions. So in this case, what is the matching answer is dou ln z by dou beta. The next problem is the ground state of the cesium atom is. See, the electronic configuration of a cesium can be written as Xe6s1. The ground state symbols, the ground state terms are calculated only from the unpaired electrons. So we have only one unpaired electron. This unpaired electron is now present in the s orbital, as it is in s orbital whose L value is equal to 0. So we have only one electron whose spin is off, and spin multiplicity, and spin is off. This is the spin multiplicity. 2s plus 1 is equal to 2, and the electron is present in s orbital. L value is 0. If L value is 0, s terms. So this is the general term symbol used to find the term symbols of different atoms and ions, where 2s plus 1 is the spin multiplicity, and L is the orbital angular momentum value, and J is the sum of the L plus A, or difference of L plus and L and S. Now here we are in s orbital. For s orbital, L is equal to 0, and for p orbital, L is equal to 1. So these are the terms which will take based on the value of L. L is equal to 0, S term will come, L is equal to 1, P term, L is equal to D term, L is equal to 3, F term. In our case, we are having the L value 0. L value is 0, then this value, L value is equal to 0. So instead of this, L is equal to 0, we can place S term. So this is the spin multiplicity. Spin multiplicity is 2, doublet, yes. So for half filled and more than half filled, the J value is L plus S. So L is equal to 0, S is equal to half, L plus S is equal to 1 by 2. So doublet S 1 by 2 is the ground state of the cesium atom. In the Born-Oppenheimer approximation, the following assumption is made. The Born-Oppenheimer approximation is based on the assumption of the separation of nuclear coordinates and electronic coordinates. Separation of nuclear coordinates and electronic or electron coordinates. In a molecular system, one can separate the nuclear coordinates and electronic coordinates. And also, as nucleus is heavier, so it will not move as fast as the electron movement. So from this Born-Haber approximation, what assumption can be made is the nuclei remains stationary in relation to the fast moving electrons. The nucleus of an atom is taken to be stationary in relation to the fast moving electrons. So the correct answer for this is option D. So for molecules, the state singlet sigma refers to. So this also is a term symbol. These term symbols are with respect to the molecules. These are the molecular term symbols. Molecular term symbols. So whatever you find here is the spin multiplicity. This would represent the spin multiplicity. So 2s plus 1 is equal to 1. So then s will become is equal to 2s is equal to 0. 2s is equal to 0. S is equal to 0. From this, we can find the spin of this molecular system. The spin is now 0. So the first statement is correct. The spin of the electrons being 0. The spin of the electrons being 0. Then both the spin and orbital angular momentum of the electrons being 0. From this multiplicity, we could say that the spin of this molecular system is 0. Then from the value of this sigma, from the symbol sigma, what one could get is the corresponding orbital angular momentum or corresponding molecular orbital angular momentum is 0. For L is equal to 0, we will use this term. For L is equal to 1, we will use pi term. For L is equal to 2, we use this delta, capital delta term. So from this symbol, we will get the value of the total molecular orbital angular momentum. Total molecular orbital angular momentum. So from this sigma, we will write the molecular orbital angular momentum to be 0. So for this term, both the spin and orbital angular momentum of electrons is 0. The correct option for this is C. Now the next problem is for the vibrational transition 0 to 1. So the band is referred to as fundamental. If this band 0 to 1 is referred as fundamental, then for the transition 0 to 2, the band is coiled. Now these are the vibrational quantum numbers. So this transition from 0 to 1 is fundamental. Then this 0 to 2 is first overtone. 0 to 2 is first overtone. Then we can also make 0 to 3. 0 to 3 is second overtone. So 0 to 2 in this problem is first overtone. Second overtone is 0 to 3. And with respect to the excited state, the transition involving the excited states is referred as hot bands. The next problem is with respect to finding the frequency, NMR frequency. A proton having a magnetogeric ratio 3 into 10 to the power 8 radians per Tesla per second is processing in a magnetic field of strength 5 Tesla. Its NMR frequency will be nearer to. So what is given is magnetogaric ratio 3 into 10 to the power 8 radians per Tesla per second. You can see this per Tesla per second. The magnetic field strength is 5 Tesla. We just for the NMR frequency, we need to just multiply these two terms. Then when we multiply these two terms, we will get this 5 into 3, 15 into 10 square. This 10 power 8 here is written as 10 power 2 into 10 power 6. The 10 power 6 is written in the form of megahertz. 10 power 6 is written in the form of M. M is mega. Mega means 10 power 6. Then Tesla and per Tesla will get cancelled. These two terms will get cancelled. Then per second is remained here. Then to get rid of this radians, we need to divide this thing by 2 pi. Then we are now left with megahertz. Per second can be taken as hertz. So 5 into 10 square divided by 2 pi is now approximately equal to, as it is nearer to 250 megahertz, which would near this value. It would not become exactly 250. It will become little less. So that is very near to 50 megahertz. The next problem, if the average separation between the adjacent lines in the rotational IR spectrum of CO molecule is 3.844 per centimeter, then the value of the rotational constant. In the rotational spectrum, the difference between the different rotational transitions. These are not the rotational energy levels. These are the rotational transitions, the transition in rotational spectrum. So energy difference between these two is 2B. These are not the energy. These lines doesn't correspond to any energy levels. These are the transitions, the energy level between any two rotational transitions is 2B, or the difference between the lines in the rotational spectrum is taken as 2B. So this value, the adjacent lines, the average separation between these two can be made equal to 2B. So these two separation is given as 3.844 centimeter. 3.844 per centimeter is equal to 2B. So the rotation constant B is equal to divided by 2. You will get this rotational constant, where B is, when B is in per centimeter, then you should take B is as H by 8 pi square by C. So this is the formula for calculating B in per centimeter units. So this is not required here. We will directly get the value of B. If the value of B is not given with respect to CO molecule, we need to now calculate the I value with respect to CO, moment of inertia, mu r square, where mu is the reduced mass. For electron configuration, in which there is one s electron and one d electron, the resultant spectral terms are. So for the electron configuration, in which we have only one electron in the s orbital and one electron in d orbital. So what is spin of this electron is taken as 1/2. Spin of this taken as 1/2. It can be, both can be plus 1/2 plus 1/2, or one is plus 1/2, other is minus 1/2, or both can be minus and minus. But by calculating the total spin, we need to always take the mod of the total spin. When both are in plus 1 and plus of, it would be s is equal to 1. The total spin of the system is 1. And total spin of the system, when one is in plus 1, other is minus 1, is 0. So this is what the two possible spin states. The corresponding spin multiplicities is this. When s is equal to 1, the spin multiplicity is 3. When s is equal to 3, the spin multiplicity is 1. So we have two spin multiplicities, singlet and triplet spin multiplicities. Now coming to their corresponding orbital angular momentum values, L value. So L value for the electron to be present in s orbital is 0. So that we will take as L1 is equal to 0. The same orbital angular momentum quantum number for electron present in d orbital is 2. For electron present in p orbital, the orbital angular momentum quantum number is 1. Now we have the electron in d orbital, L is equal to. Then the total angular momentum value L will be L1 plus L2. L1 plus L2, this would become equal to 2. When L is equal to 2, the term it takes is D. This is the term with the two spin multiples, triplet D and singlet D. So the answer for this question is singlet D and triplet D. In this problem, in a BCC lattice with the lattice constant A, the body centered position from the origin is at a distance. We need to be knowing the body centered in a BCC. How does BCC? We have a cube here, and in this is a body centered. We need to know the body centered position, which is the body diagonal. You must be knowing the 6 faces are there. Then we must imagine the body diagonal. We must imagine the body diagonal. The line which joins these two will be taken as by diagonal, or these two will be taken as body diagonal. We need to find the center of this body diagonal. Center of this body diagonal. In case of BCC, the body diagonal is equal to root 3a. So this a is the lattice constant. What you should know is, in case of BCC, body diagonal is root 3a. In case of FCC, face centered cubic, close packing, the face diagonal is root 2a. Face diagonal is root 2a. Body diagonal in case of BCC is root 3a. The center of the body diagonal. Now we have to find the center position of the origin. Center position from the origin. So this point you can take to be center. So body diagonal divided by 2. So this is the body diagonal divided by 2. Will give you center position from the origin. Root 3a by 2. So the answer for this is this. Root 3 by 2 into a. So this a is not inside the root. And also you should remember the relation between the lattice parameter and the radius of the ions, which would form different closed packed system. In case of simple cubic, 2r, a is equal to 2r. In case of FCC, root 2a is equal to 4r. In case of BCC, root 3a is equal to 4r. These are the few relations which would often be useful in finding many of the parameters. In this last problem, in a cubic crystal, the interplanar spacing of HKL planes is represented by DHKL. We denote the interplanar distance. Which of the following is true? So this is the expression we will use to find the interplanar distance. DHKL is equal to a by root, as it is cubic, then all sides are same. So we will take this to be a. When sides are different, we will take this a and divide with each of these HKL values. Then individually calculate. As it is cubic, this is the, for cubic system, we can write this to be as DHKL is equal to a by root h square plus k square plus. Now, depending on the value of the h, as a is constant, and the HKL value, the DHKL, higher the denominator, lower with the interplanar distance. So from this, whichever the option which has the lower denominator value. Now look at this option. In this option, the denominator will be root 2. In this case, denominator will be root 3. 1 square plus 1 square plus 1 square. In this case, it is 1 square plus 1 square plus 0 square. So a by root 2 you will get for this. For this you will get a by root 3. And definitely a by root 2 is greater than a by root 3. So you can check these two will not be correct. These two will not be correct. So you can check these other options also. You will find that are not correct. This is the next problem is this if the omega denotes the number of microstates. V and U are volume and internal energy respectively. Which of the following gives statistical definition of pressure P? So these are the fundamental equations one should practice for deriving many other relations. So change in internal energy is equal to TdS minus PdV, and dH is equal to dS plus VdP, dG is equal to minus STT plus VdP. That one very simple trick. If you can practice this, you can write all the three. TdS is equal to minus PdV. When you go to the next, what you should do is we need to change the sign here, as well as PdV will become VdP. Change the sign and change these two terms. PdV will become, when you go to the next term and keep it them and change here, TdS will become minus STT. And when you go to the next, this term will become will not change, and this would change. Plus VdP will become minus PdV. That's how we can practice writing this. So to start with, keep the term same and change it. And you go next, and this is kept constant and this is changed. And when you go next, this is kept constant and this is now changed. In practice little bit, you can get to know how it is written. So now for finding the pressure, we will take this relation. Helmholtz free energy, change in Helmholtz free energy is equal to minus STT minus PdV. From this equation, at constant temperature, this term will become 0. Change in temperature will be 0. So now it would get modified to dA is equal to minus PdV. So P is equal to minus dA by dV. So we have one more relation for the Helmholtz free energy. A is equal to kBT, Boltzmann constant, into temperature ln omega. So you just substitute the value of A, you will get K and K, this Boltzmann constant and temperature are constants. Taking out of the differentiation, kBT, dln omega, dou V would be the answer. So the correct answer for this question is this. KT, where K is Boltzmann constant, we have written as kV into dou ln omega by dou V. In this problem, we need to find the relation between the temperature and temperature in terms of the microstates. Which of the following gives a statistical definition of a temperature in terms of number of microstates? The relation which relates the temperature and number of microstates. For that, we have to start with the change in energy is equal to TdS minus PdV. At constant volume, this term will become 0. du is equal to TdS. And we know the relation between entropy and partition function. In this case, you can take this to be omega. Entropy and partition function, S is equal to Boltzmann constant into ln omega. Instead of this S, we will write Boltzmann constant into ln omega. Here I have written Q, you can take it as omega. So when you substitute the value of S here, you will get, as K is a constant, will be taken out, T into K, D ln Q. And you said rearrange them, you will get this form. 1 by T is equal to K into dou ln Q by dou U. So this is the relation between the omega and the temperature. 1 by T is equal to K dou ln omega by du. So the correct answer for this question is first option. So this is the end of this set of problems.